Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, like many other contributors on YouTube, our mission is to transform some of that destructive hate energy into constructive love energy for a subject that is so deserving. Mathematics is part of all that surrounds us. Just pause for a moment and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is over, and now let's get down to some serious math. This is video 4 of the video series on radicals, and I will show you how to convert a mixed radical to an entire radical and vice versa. Without further ado, let's go on to slide 1. First, a preliminary note, we're going to be converting mixed radicals to entire radicals. So point number 1, mix square root to an entire square root. Let's have a look at this square root formula that I came up with for you. Let's look at the left-hand side. Notice it has a plus minus over here. The reason for that is because I want a to be strictly positive. In other words, I want it to be strictly greater than or equal to 0. And we'll look at the b term over here. It's the square root of b. We'll call a the multiplier, and b, of course, is the argument of the square root. Now, I absolutely need a to be greater than or equal to 0, because the idea is to bring the a inside the radical. And if the a is negative, for example, -2, I cannot bring it inside the radical. So I'm going to impose the restrictions that a has to be greater than or equal to 0, and b, being the argument of the square root, has to be greater than or equal to 0. Because if b were less than 0, for example, if b is equal to -1, then the square root of -1 is not a real number. It's an imaginary number, and we'll not talk about those cases right now. So we require that both a and b be greater than or equal to 0. Now, recall that I said that a was the multiplier and b was the inside of the square root, the argument. You can think about a as being a good guy and b as being the bad guy. The bad guy is inside a square root jail. Okay? Right now, the good guy is just visiting the bad guy, but the good guy is outside the jail. The idea is to allow the good guy to come inside the jail so he can talk to the bad guy. That's the whole idea here. We want the good guy to be able to come inside the jail to be able to talk to the bad guy. Now, in order to do that, we're going to have to square the good guy. Okay, if you look at the right-hand side, we get plus minus square root a squared dot b. Now, what did we do to get the a inside the square root jail? We had to square it. You can understand this more fully if we try to read the square root formula backwards. Okay, a squared is a perfect square, and it's also positive. In other words, the a is greater than or equal to 0. So that means the square root of a squared dot b can be rewritten as a dot the square root of b. Because the square root of a squared is a, you can bring it outside the radical. Okay, so that means that the right-hand side becomes plus minus a dot the square root of b. And of course, that's exactly the left-hand side. Okay, so the left-hand side and the right-hand side are essentially equivalent. So to recap, in order to let a positive good guy inside a jail that contains a positive bad guy, we need to square the good guy. Okay, now the left-hand side over here is called a mixed radical because a is non-radical and the square root of b is radical. Whereas on the right-hand side, this is an entire radical because all the components are inside the square root. Okay, So the objective is to go from a mixed radical to an entire radical. And again, the way we do that is by squaring the good guy on the outside to allow him to open up the jail door and come and visit the bad guy on the inside. And there he is. There's the good guy squared times the bad guy. And that's the only way a good guy that's outside the jail can gain entry to the inside of the square root jail. Okay? And again, A and B have to be greater than or equal to 0. Okay, so let's go through an example over here. 2x squared dot y, we identify that with A, the multiplier, the good guy. And then we have the square root. And then we have 3x cubed dot y squared. We identify that as the bad guy inside the square root jail. The objective is to allow the good guy to open the door of the jail and come inside and visit the bad guy. Again, in order to do that, we have to square the good guy. So we grab this, bring it inside the jail, and square it. Now, once it's inside the jail, we can use exponent laws to simplify the situation in here inside the jail, because we have the original bad guy over here and we have a good guy squared in front. So we can easily use exponent laws to simplify that. First of all, we have 2 to the power 2, which is 4, and 4 dot 3, which is 12. And there's the 12 right there. Then if we look at all the x terms, we have x to the power 2 dot 2, which is 4. And then we have x to the power 3, so you put down a 3. And then let's look at the y terms. We have y to the power 2. There's the 2 right here. And then we have plus 2 from the bad guy. So we have y to the power 2 plus 2 altogether. If we continue to simplify, we get square root 12 dot x to the power 7 dot y to the power 4, and we are done. So we've converted this mixed radical into an entire radical. In other words, this radical contains, it's like a jail containing everything. Okay? Again, this was mixed because we had a good guy outside and we had a bad guy inside. And we allowed the good guy inside the radical. We squared it. Then we used exponent laws to simplify to get this as our final answer. Okay, so on to the next slide. Now part 2 over here deals with general mixed root to a general entire root. Okay, so if we look at the left-hand side again, we get plus minus a dot. The cth root of b is equal to plus minus the cth root of a to the power c dot b. And I call this the general root formula. So we've gone from a mixed radical here to an entire radical here. We leave the plus minus on the outside. Okay, now how did we get the a, which is the good guy, inside the cth root jail in order to visit the bad guy? In order to do that, we have to raise a to the power c. So we have a to the power c dot b. Think of it the other way around. A to the power c, the cth root of that is just a. So that the a gets extracted on the outside. Again, the cth root of a to the power c is just a, so it can come outside the jail. Okay, and that's exactly what I have over here. So the left-hand side is exactly equivalent to the right-hand side. Now, this time we're going to assume C can be even or odd. C is called the index of the radical. C can either be even or odd. Like, for example, if C is even, it could take on values like 2, 4, 6, 8, etc. And if C is odd, it can take on values like 3, 5, 7, etc. Now, when C is even, we require that both a and b be greater than or equal to 0. And that happens in order to avoid imaginary numbers. Otherwise, we're going to get imaginary numbers. Okay, when c is odd, we don't have to worry about getting imaginary numbers. And there is no restriction on a and b. Okay, so when c is even, we have to restrict a and b to be both greater than or equal to 0. However, when c is odd, we need not impose any restriction on either a or b. Recall that a is the multiplier and b is the argument of the radical. So a is the multiplier and b is the argument of the radical. Okay, so let's look at an example here. We have 2x squared dot y dot cube root 3x cubed dot y squared. We identify the 2x squared dot y as the multiplier a. That'll be the good guy. And then we get cube root. So the contents or the argument of the cube root we identify as b. So 3x cubed dot y squared will be the b. Okay, in order to allow the good guy to come and visit the bad guy inside the cube root jail, we necessarily have to cube the good guy. And that's exactly what I did. Okay, so there's the good guy there. We have to cube it. There's the bad guy there. And again, we use exponent laws to simplify the argument of this cube root. When we use exponent laws, it becomes 2 to the power 3, which is 8. And 8.3 is 24. There it is. And then we have x terms. We get x to the power 2.3, which is 6. There it is. And we have a plus 3. There it is. And then finally, we have y to the power 3 plus 2. Y to the power 3 plus 2. And so if we simplify that a little bit further, we get cube root 24, x to the power 9, dot y to the power 5. And we are done. Essentially, this is a mixed cube root. And now we have an entire cube root. And this is exactly the way we go from a mixed radical to an entire radical. Do not forget about these restrictions. You know, I'm not going to mention these restrictions anymore, but beware that these restrictions are to be understood. Okay, so let's go on to the next slide. Now we're going to actually be using the square root and general root formulas in order to convert mixed radicals to entire radicals. Okay, so if we look at question 1a, we have a minus 2x square root 3 dot y. The assumption over here is that x is positive, so we're going to leave the minus sign outside. And the assumption here is that y is positive. Otherwise, we have the square root of a negative number here. Okay, so to bring the 2x inside the square root, we have to square it. And then when we use exponent laws, we get minus 2 squared is 4 dot 3 is 12. And then we have x to the power 2 dot y. And that's the final answer. Notice that we had to leave the minus sign outside the radical. There is no way you can bring that minus sign on the inside of the radical. Okay, so we leave it alone. And that'll be your final answer. This is the entire radical. Let's look at part B. We have a dot b, square root a squared dot b. We identify the good guy as a dot b. The bad guy is a squared dot b. To bring the good guy inside the jail, we have to square it. And that's what we do. And then we use exponent laws to simplify the inside of the jail. When we use exponent laws, we get a to the power 2 plus 2, dot b to the power 2 plus 1. When we continue to simplify, we get square root a to the power 4 dot b cubed, and we are done. Again, the assumption is that the product a dot b is positive, and the product a squared dot b is positive. Okay, let's go on to part C. We have 1/2 dot y dot square root 8 dot y to the power 4. We assume that y is positive, and of course the argument of the square root is already positive because y to the power 4 is always positive. So we don't have to worry about that. But essentially now the good guy over here is 1/2 dot y. The bad guy is 8 dot y to the power 4. We want the good guy to come inside the radical or inside the jail. In order to do that, we have to square him. So we get square root y over 2 all squared dot 8 dot y to the power 4. And again, we can use exponent laws over here to simplify. Over here, we get, on the bottom, we get 2 to the power 2, which is 4, and then 8 over 4 is 2. There it is. And then for the y term, we get y to the power 2 plus 4. So we get y to the 2 plus 4, which is y to the power 6. So altogether, we have square root 2 dot y to the power 6, and that's your final answer. Again, this is a mixed radical. That's the entire radical. And we're going to go on to the next slide. This is a note on how to convert entire radicals to mixed radicals, the other way around. In the last slide, we were dealing with questions where we were going from mixed radicals to entire radicals. Now the idea is to start with an entire radical and reduce it to produce a mixed radical. Point number 1 deals entirely with square roots. So we're going to be going from an entire square root to a mixed square root. And this is called reducing radicals. We have the square root of a squared dot b. Of course, a squared is a perfect square, so the square root of a squared is just a. We can bring it outside, and we get a dot, the square root of b. I call this the extraction formula because essentially we're extracting the a from the jail. Recall that I call this a jail. We have a good guy. The a is the good guy. You have to square to come inside the jail, and then we have a bad guy right here. In order to let the good guy outside the jail again, you have to do a square root, or you have to perform a square root. So the square root of a squared is a. You put it on the outside, and we get a dot, the square root of b. So again, I call this the extraction formula. And where we assume we've got some restrictions over here that a and b have to be both greater than or equal to 0. Okay, so the a over here, which is the good guy, and the b, which is the bad guy, have to be both greater than or equal to 0. And also, we want to ensure that b is irreducible so that the square root of b, the square root of b must be irreducible. So in other words, we cannot extract any more perfect squares from the bad guy. Okay, so we'll see how that pans out in the example. So here's an example. We have the square root of 12.x to the power 4.y cubed z to the power 7. That's an entire radical, and we're going to try to reduce this entire radical to a mixed radical. And essentially what we're looking for is perfect squares here. Okay, now 12 is not a perfect square, but it can be written as 4.3. 4 can be written as 2 to the power 2, so we drop in a 2. X to the power 4 is a perfect square, and the square root of x to the power 4 is x squared. We drop that in there. Now y cubed is not a perfect square, but it can be written as y squared dot y, and y squared is a perfect square, and the square root of y squared is just y, so we drop it in there. Z to the power 7 is not a perfect square, but it can be written as z to the power 6 dot z, where the square root of z to the power 6 is z cubed, so we drop in a z cubed here. Okay, and of course we have to square everything. So there's the good guy right there. Now let's see what's left over. We have a 2 squared is 4. We know we need a 12, so there must be a 3 left over. We get x to the power 2 squared is x to the power 4. And we had x to the power 4, so we don't need an x on the outside. We have z to the power 6 compared to z to the power 7, we need another z on the outside. So we identify the inside of the round brackets as the good guy and the outside as the bad guy. And now it's time to extract the good guy squared from the radical. Of course, the square root of anything squared is just that anything, and we're going to bring it outside the radical and leave the bad guy inside the radical. So here's the good guy outside the jail, and there's the bad guy. He's still in jail, and he cannot be extracted. So in this case over here, we had the good guy visiting the bad guy inside the jail, and then when all was said and done and the conversation was over, we let the good guy outside the jail again, and there he is here, and we have the balance is the bad guy. Okay, so we identified the good guy here. We let it outside the jail by taking the square root, and we're left with the bad guy that continues to be inside the jail. Again, we have an entire radical here and a mixed radical here, and this is called reducing radicals. So let's go on to the next slide. Now, point number 2 will be going from a general entire root to a general mixed root. Okay? So a general entire root may look like the cth root of a to the power c dot b. We identify the a as the good guy because the c's match, and we identify the b as the bad guy. Now the cth root of a to the power c is just a. That's how we extract the good guy from the radical, and then we're left with b as the bad guy. Okay, so again, this is an entire radical, and this is the mixed radical equivalent of the entire radical, and I call this the extraction formula. And then we have some assumptions that we have made. Now when c is even, for example, the c over here could be 2, 4, 6, 8, etc. The c here and the c there. It requires that a and b be both greater than or equal to 0. In other words, the good guy has to be greater than or equal to 0, and the bad guy has to be greater than or equal to 0. Otherwise, we start getting into complex numbers. On the other hand, if c is odd, we require no restriction. There's no restriction when c is odd. And we assume that the cth root of b is completely irreducible. In other words, we've extracted the largest possible good guy from the inside of the radical. That makes the cth root of b irreducible. So let's look at an example over here to see how this works. We have the cube root of 24x to the power 4 dot y to the power 8 dot z to the power 5. Okay, now the idea is to be able to write this entire radical as something of the form a to the power c dot b. In this case, the c value is 3. So what I do is open up a big cube root bin, and I open up empty brackets over here, and I put power 3, and I leave this empty. This will be the balance, which will be the bad guy that's left inside the cube root jail. Now, the thinking process goes like this. 24 is not a perfect cube, but we know that 24 is 8.3, but 8 is a perfect cube. The cube root of 8 is 2. We drop it inside the cubed bin. Now x to the power 4 is not a perfect cube, but x to the power 3 is. So we can drop, and the cube root of x to the power 3 is of course x, so we can drop in an x in there. Now y to the power 8 is not a perfect cube, right? But y to the power 6 is. And the cube root of y to the power 6 is y squared. We just drop it in there. And next, z to the power 5 is certainly not a perfect cube, but z to the power 3 is. And the cube root of z to the power 3 is just z. So we finished with the good guy. and it's the good guy, needs to be cubed. Now, how do we get the balance? The balance will be the bad guy. Okay, don't forget that this part over here is blank for the time being. And we'll work things out. We get 2 to the power 3 is 8, but we need a 24. To get a 24, we need a 3 here. We get x to the power 3, but we need x to the power 4, so you have to tack on an x here. We get y to the power 6, but we need y to the power 8. So you have to tack on a y squared term here. And then we have a z to the power 3, but we need z to the power 5. So we have to tack on a y squared term here. So now we can identify the inside of the brackets as the good guy and the outside of the brackets as the bad guy. So it's time to extract the good guy outside the radical. And of course, all you do is copy paste the inside of the brackets, put it outside, and the good guy or the bad guy over here is what's left over inside the jail. And the cube root of 3xy squared dot z squared is then irreducible. Okay? Remember we said that the cth root of b should be irreducible. That's how you know that you've extracted the largest possible perfect cube outside the radical. Okay? This cube root here at the end must be irreducible. Okay, let's go on to the next slide. And let's do some questions that pertain to converting entire radicals to mixed radicals. Part A, we have square root 4m cubed. Okay, in order to extract the largest perfect square, I open up a square root like so. Open up empty bin to the power 2 and leave this out. I know that 4, the square root of 4 is 2, drop in a 2. I know that m cubed can be written as m squared dot m, and then the square root of m squared is m, drop in the m. And now to figure out what the balance is, and of course the balance is going to be the bad guy. So we have 2 squared is 4, we get a perfect match. We get m to the power 2, we need m to the power 3, so we need an m right here. Okay, so we have a perfect square. So we identify the 2m as the good guy, and then we have the bad guy, which is m. So it's time to extract from the square root and bring the good guy outside the jail. So all you do is copy paste the inside of the brackets, put it outside the jail. What's left over is the m. And this is the mixed radical. Again, this was the entire radical, and this is the mixed radical, and we're done. Let's look at B here. Same sort of problem. We have a 20.a squared.b. So you open up a square root, open up an empty bin, raise it to the power 2, leave this blank. And 20 can be written as 4.5. The square root of 4 is 2, drop it in. A squared, the square root of a squared, I know is a, drop it in. And of course the square root of b I don't know, so that goes on the outside. So pretend like you don't know anything over here. We have 2 to the power 2 is 4, but we need a 20. So we need a 5 on the outside. And then a to the power 2 is just a to the power 2. We don't need any more a's over here. And of course b was left over, so we get a 5.b. So the good guy is 2.a and the bad guy is 5.b. It's time to let the good guy outside the jail, so copy paste, and we get 2a on the outside, and we're left with a 5.b on the inside. Okay, so we're done with that. Let's look at part C over here. Same sort of problem. We have the square root of 12.x cubed dot y. Now 12 can be written as 4.3, and we know the square root of 4 is 2. But before we even do that, open up a square root, Open up a set of brackets, raise to the power 2, and leave this blank. Okay, again, 12 can be written as 4.3. Now the square root of 4 is 2. You can drop it in. And then x cubed can be rewritten as x squared dot x. The square root of x squared is x. Drop it in. And of course, the square root of y, I don't know what that is, so you have to leave that alone. And now 2 to the power 2 is 4. We need a 12, so we have to drop in a 3. And x to the power 2, we need x to the power 3, so you have to drop in an x. And of course, y was left over from before. So we identify the good guy as 2.x, and the bad guy is 3.x.y. Now we extract the good guy from inside the jail. We let him outside the jail. And we get, so all you have to do is copy paste the inside of the brackets, and we get 2x dot, and what's left over here is 3x dot y. Okay, so the good guy came out, and what's left is the bad guy, and that's a mixed radical. So let's go on to the next slide. Again, more of the same thing. Question 3a. We have the square root of 50 dot m squared dot n cubed. And what I do is open up a large square root, open up empty bins, raise to the power 2, and leave this blank. Now 50 can be rewritten as 25.2. The square root of 25 is 5. Drop it inside the bin. M squared, the square root of that is m. Drop it inside the bin. And n cubed can be written as n squared dot n. And then the square root of n squared is just n. Drop it inside the bin. So we're done with a good guy here. Now, to figure out the bad guy, we do 5 to the power 2, which is 25. Compare it with 50, we need a 2. And we do m to the power 2, compare it to m squared, we don't need an m. Then we'll do n to the power 2, compare it to n cubed, and we need an n. So we identify the bad guy as 2.n. So we have the good guy squared over here. We're going to extract it. We have a 5m.n, and what remains is the bad guy inside the jail. So this is the mixed radical. Let's go on to b. We have square root 18.a.b cubed. Again, you open up a big square root, open up an empty bin, raise to the power 2, leave this blank. 18 can be rewritten as 9.2. Now the square root of 9 is 3, drop it inside the bin. The square root of a, we don't know what that is, so leave it alone. But b cubed can be rewritten as b squared dot b. The square root of b squared is b, drop it inside. Okay, now we got to try to figure out what the bad guy looks like. We have 3 to the power 2, which is 9. We need 18, so we drop in a 2. We have b to the power 2. We need b cubed, so drop in a b. And of course, the a was left over. So we can identify the bad guy as 2.a.b. And of course, 3b squared is a perfect square. So we can extract it from this square root. And we get 3.b dot square root of 2a.b. Okay, recall that 2a.b is the bad guy, and he is inside the jail and cannot come out. Okay, so C, we have square root 9.e to the power 4 dot f to the power 6. And again, we open up a big square root, put an empty bin over here, raise to the power 2, and leave this blank. Now, square root of 9 I know is 3, put it inside. The square root of e to the power 4 I know is e squared, put it inside. And the square root of f to the power 6 I know is f to the power 3. And lo and behold, we have nothing left over. Let's check it out. 3 to the power 2 is 9. There it is. E squared to the power 2 is e to the power 4. There it is. F cubed to the power 2 is f to the power 6. There it is. And it turns out that the inside over here was indeed a perfect square. So we're just left with essentially a 1 out here. Okay, so we take the good guy, bring it outside the radical. we get a 3 dot e squared dot f cubed. And of course, we're left with the square root of 1. And we know the square root of 1 is just 1. So we're just left with 3e squared dot f cubed as the final answer. Okay, let's go on to the next slide. Again, for question 3, we're going to be converting from an entire radical to a mixed radical. So let's look at D. We have the square root of 10 dot x to the power of 5 dot y cubed. Again, we're going to do the same sort of thing we did before. Open up a big square root, open up an empty bin, raise to the power 2. And then I see that I can't break down 10 as a perfect square times a non-perfect square, so I can't do anything there. But x to the power of 5 can be decomposed as x to the power of 4 dot x, and the square root of x to the power of 4 is just x squared. And y cubed can be decomposed as y squared dot y, and the square root of y squared is just y. Okay, so we're done with the inside of the brackets. Now let's try to figure out what the bad guy is. Okay, the good guy is x squared dot y. We need to figure out what the bad guy is. So, I know the 10 I couldn't do anything with, so it's definitely a bad guy. And then we have x to the power of 2 dot 2, which is 4. We need x to the power of 5, so x is part of the bad guy. And then we have y to the power of 2, and we need y to the power of 3, so y must be part of the bad guy. So we have the good guy is x squared dot y, and the bad guy is 10x dot y. So we have to extract from the radical now, just copy paste the inside of the brackets, and you get x squared dot y on the outside, and what remains is the square root of 10x dot y. And of course 10x dot y is the bad guy, and we have a mixed radical. Now part E over here is a little bit on the tricky side. Forget about converting this entire radical to a mixed radical for now. We have the square root of minus 40 dot x to the power of 3. We already have a minus sign here. We know that the argument of any square root has to be greater than or equal to 0. So if this is already a negative in here, in order for the argument to be greater than or equal to 0, then x has to be negative. Okay, for example, if x is equal to negative 2, then we have negative 2 cubed is minus 8, and then we have minus 8 times minus 40, which is positive 320, and we're good to go. So the point is that if you have a minus sign out here, that automatically implies that x has to be negative. Okay? So if x is negative, the only way to make it positive is to put a minus sign in front of it. So it's a tricky example here. So anyway, we open up a big square root, and we open up an empty bin, we raise to the power 2, and we figure out what to put in here. Let's look at the 40. 40 decomposes as 4 dot 10, the square root of 4 is 2, drop it inside. And then x cubed decomposes as x squared dot x. And then the square root of x squared, you would think, is x, not true. Okay, so you can't do it like that, because the square root of x squared is not x, because we already said that x was negative. Okay, so we have to put the negative inside here. So now minus x is positive. If x, for example, is negative 3, then minus 2 times negative 3 is positive. And that's exactly what you need over here. So that minus sign has to be coupled with the x. Be very careful here. Otherwise, your result will not be correct. So now let's try to figure out what's left over. We need to figure out the bad guy here. Minus 2 squared is 4. We need a minus 40. So obviously we need a minus 10 over here. Then we get x to the power 2, but we need x to the power 3. So we need an additional x out here. So now the good guy is minus 2 dot x. It's going to be extracted from the radical. And the bad guy is minus 10 dot x. Okay, so in doing that, You have minus 2x, which is the good guy, and square root minus 10 dot x, which is the bad guy. Notice that minus 2 dot x is positive because we already said that x had to be negative. And minus 10 dot x is also positive because we said that x had to be negative. Okay, for example, if x is negative 3, this becomes 6, which is perfectly legitimate. And if x is negative 3, this becomes the square root of 30, which is perfectly legitimate. So go over this question carefully, okay? It's a trick question. For part F, we have the square root of a to the power 4 dot b all over 4. Just a little fraction here. We're going to do the same thing. We're going to open up a big square root. We're going to open up an empty bin, raise to the power 2, and leave this blank. Now, the square root of a to the power 4 I know is a squared, and the square root of 4 I know is 2. And the square root of b I can't do anything with. So now, let's work this out to see what the balance has to be here. A to the power 2 to the power 2 is a to the power 4, perfect. And over here you have 2 to the power 2, which is 4, perfect. And of course b is the bad guy. Okay, so we have a perfect square over here. We identify the good guy as a squared over 2, and the bad guy is b. Now you want to extract the good guy from the square root jail. So all you do is copy paste the inside of the brackets. You get a squared over 2, and then what's left is the square root of b. And then you can make this look a little bit more cute. It looks a little bit ugly there. So to beautify it a little bit, just put down a squared dot square root of b all over 2. Again, this move over here is completely optional. I don't care one way or another whether you perform this move. I just thought I would show you how to do it. Anyway, I think I'm going to do an over and out for this video. Thank you. Take care. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from Ernest at MathLab Tutorials in Toronto.